Okay, hope the screen is visible. Uh, I hope all of you have already watched the lecture series. Then only you people can understand more easily the problems today I'm solving. And first of all, what is an activated sludge process? I hope you guys have seen like what is exactly the system and how this is working. But still, I will give you what. Okay, still, I will give a short, description about the whole system of a conventional uh, activated sludge process. First of all, okay, in the system we have primary treatment. So primary treatment is used mainly to remove the big size particles and the if there is some solid things are present, plastics are present, or like big grills are present, then it can remove in the primary treatment process. Then it comes the primary settling tank. Primary settling tank. So in this primary settling tank, we'll give some time to the wastewater, and uh, because of and also the flow is also reducing. Flow velocity is also reducing, so that some of the sludge will settle down in the bottom part because of gravity, and also the flow velocity is reduced, so the big sized sludges settle down, and this can be removed, and the remaining solution is flown to a aeration tank. So in this aeration tank we are providing air, and there will be microorganisms present, and what happens is the microorganisms consumed uh, the organic present in the solution, and then degrade, and also it will form a big sludges, because it will eats the food that is available, and also form big sludge particles in this particular tank. And then what is happening, we will flow this whole system flow to the secondary settling tank. This is secondary settling tank. So here what happens, the solution which is reached in the settling solution secondary settling tank, like the primary settling tank, here also flow velocity is reduced, and then the bigger sludges will settle down in the ground in the bottom part, and this can be removed. So one thing here is, this sludge either we can remove like a waste, or this sludge can be taken and then returned to the aeration tank, and can be again used in this tank. Because in the sludge means, in sludge, what exactly the composition of a sludge, anybody can tell what is a sludge actually? Biomass, yes, that microorganisms are there, yes, and also water content is also there in the sludge. We should mention water content and also microorganism. So this microorganisms, if we take the sludge and provide in the aeration tank, and again this particular system will be active. So active because of the presence of microorganisms. So either the sludge can be removed like waste, or this can be re-inhibited to the aeration tank for the active process. Then the remaining water, which is somewhat clean can be given to the last step. What is this last step, you know? This is disinfection, the disinfection unit. So first of all, primary treatment. Primary treatment means in the wastewater, if there is big particles and plastics or something is present, this can be removed in the primary treatment. And this primary treatment is really required, because otherwise your entire system will be affected by the presence of big particle, which will reduce the efficiency of the system. And so that the primary treatment is much important. The primary treated wastewater is given into the primary settling tank, where the sludges will settle down due to the gravity. Also here the flow velocity is reduced, and then the remaining wastewater is given to the aeration tank. Here we provide enough air, so that the bacteria, not only bacteria, the whole microorganisms can get the proper situations where they can eat the food and multiply. And then the whole wastewater is given into the secondary settling tank, where the sludge will again settle down. And this sludge can be, we can like give as a waste, or this waste we can use as a fertilizer also. Or we can give this waste sludge to the aeration tank as a recycle, and the remaining water is given to the next step, that is the disinfection step. This is the whole unit of an conventional activated sludge unit. So what exactly this activated sludge, anybody can tell what is activated sludge? So here the main aim is, we need microorganisms. We need microorganism which can, take the organic content in the wastewater and degrade it and make a sludge, and then we can remove the sludge. So we need microorganisms which is more hungry. So hungry is the main thing here for the microorganisms. If the microorganisms are more hungry, what it do, like it will consume more food. More food means we are actually treating the wastewater more effectively. We need hungrier microorganisms for this operation. How do you make microorganisms hungrier? Anyone can tell? So how do you make, we need hungrier microorganisms, because we need to consume the, see that the TDS in the, in our system to make pure water. So anyone can tell that how we'll get more hungry microorganisms? What is the how we make them hungrier? So how to make this microorganisms hungrier, more hungry? So the first thing is, what are the conditions here? If a wastewater have low dissolved oxygen, so if there is low dissolved oxygen, then what happens, the microorganisms cannot have the proper uh, degradation step. So the microorganisms, they are having a tendency that when there is a proper do is come to the system, it has a more tendency to eat or consume the food in a very high rate. That is, the metabolism increases when there is more do is introduced to the system. And also, if the nutrient is less, initially, if the nutrient, for example, nutrient means nitrogen, phosphorus, if this nutrient is less in the wastewater, then what happens, the microorganism don't get, means they don't get that nutrient to consume as food. So these are microorganisms will be more hungrier. Then third is, also we'll have more aeration time. Aeration. So if the aeration time is more, if aeration time means that is, it, the microorganisms are exposing to the low nutrient conditions, exposing to low nutrient conditions. So microorganisms are exposing to low nutrient condition. So at this particular situation, this microorganisms will be very hungry. That time they will be, that time they were waiting for the, suitable situation where they can eat or consume food in a vigorous manner. So then also we can say about the wastewater amount, wastewater composition. So here in the wastewater only, if there is more nutrient or more organic loading is there, then the microorganisms are, at a rate of eating it more. They are consuming the food and they are in a good state of multiplying, and then they are in a good state. But when the in the water composition, if the enough nutrients or the needed things are less, then those micro that those that time microorganisms are in the low metabolic state, and they were waiting for a suitable environment for their increasing the metabolism rate. So at this time, also about, at this particular time, even the microorganisms start consuming other microorganisms also, because of this hungry. So at this particular hunger time, when we provide the wastewater for for treatment, then they were very high metabolic rate and they start consuming the presented nutrient organic thing very vigorously. So this is the, that's what here we need microorganism which are in a hungry, so that the our wastewater is properly treated. Okay, so first question, secondary treatment of wastewater effluent is usually achieved through four are given, options are given. um, Physical, chemical process, biological process, chemical process, all the above. So secondary treatment is what? Anyone tell? Anyone can tell? Secondary treatment of wastewater effluent is achieved through, the answer is biological yes, yes. So what is this physiochemical processes? Yes, that is, yes, that is the primary process, right? And this biological is secondary. And what is this chemical processes? This is tertiary. So here only disinfection comes. Also, we remove the toxicity, and these all things comes under tertiary treatment. That is the chemical process. Okay. So next question: a temperature range of 45 to 70 degrees more suitable for the growth of they have given three four different types of organisms. So which one is uh, 45 to 70 degree temperature is which? Yes, 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 true. Yes. Okay. So here I will upload this PPT so you can refer this slides. So then this the temperature suitable range is given, and also this left this right hand side shows the thermophiles produce some of the bright colors of Grand Prismatic Spring Yellowstone National Park, so that you can see. And here, this graph shows the classification of microorganisms by temperature requirement. So here you can see from psychrophile, mesophile, thermophile, hyperthermophile, and hyperthermophile at what temperature is suitable for their growth, that you can refer from the slide. So next question. Essential requirement for the growth and survival of microorganisms is, so four options are given: source of energy, source of carbon, nutrients, and inorganic. So what is the essential requirement for the growth and, yes, all the above. Yes, true, all the above. We need source of energy, we need carbon, we need nutrient and inorganics. So next is, here we see that in the monod equation, mu is equal to max s by ks plus s. The term here ks represent to what? What is the ks here? So you guys would have watched the lectures, na? So can you answer this question? Yes, yes. Yeah, this is the, yes, this one. So here you see that mu is equal to mu max s by ks plus s. This is the monod equation, and here mu is specific growth rate of organisms per hour or per day. It can be mentioned. Mu max is the maximum specific growth rate, representing the highest rate of microbial growth when the substrate is not limiting. S is the substrate concentration. Substrate means here BOD, COD, or any other limiting nutrient. Ks is the half saturation constant. So here we can interpret this. We'll vary Ks and Ks, and we can actually find some relation in this equation. Normally here mu is equal to mu max S divided by Ks plus S. So here the first interpretation, low substrate concentration. Low substrate concentration means here substrate concentration means what? So concentration of BOD, COD, or any other nutrient. So here if this substrate concentration is very much low compared to Ks is the half saturation constant. So if this particular condition is there, how can we rewrite this equation? So here S is very small. So this S is very small. So mu can be written as mu max into, this is very small. So for example here we can write this one, this particular is very small, and here this particular is, we can write like this is very small, so we can eliminate this term. So because since this is very high, if we adding with this value ks to a small value, yes, there is no point, I mean there is no meaning, but here in the numerator it does matter. So we can write like this. Got it? This relation can written like this at this particular, if there is a question comes like at low substrate concentration, this particular relation we can write like this. So this equation you can use to solve the questions if this particular condition is there. So this you understood now. For example, this yes is, I'm just writing like for understanding I'm writing 0.00001, and here ks means like 10 or 10 or something. So when you add with this, if this is ks, So if you add 10 with this 0.00001, it doesn't matter in the denominator, but in numerator it does matter. So that's why we can write this equation at this low substrate concentration in this manner. Okay, this is the one thing. Next thing, at high substrate concentration. So high substrate concentration means what? So at this particular time, BOD and COD or any other nutrient is very high. This S is very, very high compared to KS, half saturation constant. So at this time, how can you write this equation? So S is very high, this is very high, S is very high, and K is very small. That means mu is equal to mu max into this S divided by K is very small, so you can eliminate in the denominator. So this become S. So this get cancelled. So mu is equal to mu max. So this particular situation, see, at high substrate concentration, this monod equation can be written like mu is equal to mu max. So this you can read and understand what I have explained you now. Okay, so if some questions, if some problems comes at this two different situation, you can easily calculate. You can directly like either this equation or this equation and you can solve the question. Now, next question. Which one? Yes. Fine. Okay. So now next question. So a greater value of F by M. What is F by M? What is F by M? Food to microorganism. Yes, right. So here the greater value of F by M ratio can be obtained by four options are given: decreasing effluent BOD, increasing sludge wasting and reducing sludge recycling. See both A and B, and D none of the above. So what will be the option? So we need a greater value of F by M. So either for this particular situation, we need F value high or M value we can decrease. So according to that, what is the option which is more suitable here? So here you can see in the graph. So this is, see, high food to mass ratio. This is ideal and this is low ratio. So in this high food is to microorganism ratio, here you can see food. Food means here I told you. So here, if food is high, and here this is the microorganisms are less. So this quantity is less and this quantity is high. So that's why high F is to M ratio. So here when it comes to low ratio, what we have to we have to decrease the food, or we can also increase the microorganisms. Here you see in this particular graph, you see this particular line denotes the food. So here we decrease the food. So that's why here we can achieve lower ratio. So coming back to question, a greater value of F by M ratio. That means we need either higher food or we need lower microorganisms. How do we achieve from these options? Anyone? Can answer. Yes, right, right. This is the yes, you're right. This is the answer. How do you are doing? So you here from the primary, this is the primary settling tank. Then what you are doing is to the aeration tank. I'm just giving a short note here, the aeration tank, and then there is microorganisms and that will consume food, and in the secondary it will settle down, right? So either in the settle down it will go for the waste, or here also it can be recycled to the aeration. So what they are saying is increasing the sludge wasting. So increasing the sludge wasting means we are removing more sludges. More sludges removing means what exactly meaning? Sludge has microorganisms. Sludge means it has microorganisms, right? So we are actually removing the microorganisms. More waste we are removing. That means the sludge which is in the secondary settlement tank, we are removing rather than giving for the recycling in the aeration. We are actually reducing the microbes, right? So we are achieving by this point decreasing the microbes by removing it from the secondary settlement tank. So if you increase the recycling means you are providing more microbes to the aeration tank, but what you are doing is you are reducing the sludge recycling, reducing the microbe supply here, and you are removing the sludge and you are taking it as a output here. Got it? Okay. Okay, so next question. uh, so here you can see this problem and you can solve after that, after I upload. And here you can see in this question, f by m ratio is equal to q into BOD into 10 to the power minus 3 divided by B into dash. So what is the, what we can write it here? Yes. You can see this question also. Understand that they have given the values and how they are calculating f by m ratio. Q is given, Q is the average daily flow, and BOD average BOD of settled sewage, and MLSS mixed liquid solids, and aeration basin volume is the V. So here Q, what we have to add here? Yes, yes, yes. Here MLBS. Yes, yes. So this problem you can try to solve. The answer and everything is given. And here, next question, what is called sludge volume index? What is the sludge volume? What is the term sludge volume index is used to determine? Four options are given: settling characteristics of sludge, volume of sludge, degradation characteristics of sludge, or none of the above. Which one? So here, yes, settling characteristics is the answer. So we are using the sludge volume index. So seeing the sludge volume index, we'll get to know what is the settling characteristics of the sludge, where the system will, properly worked after during the operation, and how we can control the system, and all this from the this SBI we'll get to know for the further process optimization. The sludge oleum index is the oleum in milliliters occupied by 1 gram of activated sludge which has settled for 30 minutes. So we'll measure the volume of sludge which is settled for 30 minutes. So then seeing that volume, we'll get to know you can further process the optimization of the proper working of your whole system. So this you can read. Now, next question. The salient features of an activated sludge process is what? Aeration, biomass recycling, waste activated sludge, all of the above. Which is the salient features of? Yes, right, all of the above. Because all these processes are there in the system. Next question. Which one of the following bioreactor configuration is the basis for trickling filter? What is trickling filter? Okay, then what is the okay? See, yeah, right. Fixed bed attached growth. So here, what is doing there? What in trickling filter? See here, the microorganisms are attached to the medium, and then the components back down, organic components in the wastewater. The system is designed to allow air to penetrate, promoting aerobic microbial growth in the upper layers and aerobic growth in the lower region. So here in the trickling filter, there is a medium. So what are the different types of mediums we can use? See, we can here they are using the gravels. So even you can use the plastics also, where the microorganisms are attached and grow, and from the wastewater it gets the food and it will degrade the wastewater, and the settling sludges we can collect it, and the aeration is also we can provide in the layers. So here, what is the tricking filters can reduce the amount of organism in wastewater, allowing treated wastewater to the discharged into rivers or ocean. So here you can see from here center it is coming, and the wastewater we are you are providing to the media. Here, and this particular medium has the microorganisms, and it will eat the food from the wastewater, and the sludge which is formed, it is settling and we are removing it, and the remaining water is sent to the rivers or oceans, and this is the process of the trickling filters. And here you can see different so I have written the steps of the trickling filters that you can read. So now next one is rotating biological contractor. So in a rotating biological contractor, water is passed through the packed bed media is passed through the water. Both water and media rotate in the counter current direction, none of the above. So what is the option? in a rotating in a rotating biological contractor, uh, so how what is the option for that? Yes. See, I thought this is, yeah, yes, the media is rotating, and the so here you can see this is the structure, and this is the media, this packed media, it has the microorganism, and it is rotating in the water. So here you can see the structure, A large cylindrical drum or series of large discs mounted on the horizontal axis. The drum or disc it is partially submerged. You can see this particular portion is exposed to the air. So actually this will come, like while it is rotating, it will be in contact with air again in the wastewater, like that it is rotating. The disc or drum have the surface where the microorganisms, so here the microorganisms will grow. The surface might appear textured. Okay, this is biofilm. Biofilm means what? Yes, layer of microbes. So yes. So here, an rotating mechanism, the central axis or shaft of the disc or drum, causing them to intermittently expose to the air and the wastewater. So here, when it rotate, it will rotate like that. It will be in contact with air for some time, and then again with the wastewater, like that it is rotating. Then the tank or basin holding the RBC is usually rectangular or circular with the inlet and outlet of the wastewater. See here you can see the inlet, and then it will have an outlet for the settling tank, and then we can collect the effluent. So aeration you might see. So aeration is needed. So why this aeration is needed? Yes. So microbes need oxygen, so that we need aeration also. So that this is actually we are providing the aeration also. So here, uh, so I have written this answer. Packed media is passed through the water. So this I have. Yeah, but see, I will check you since you are saying that counter current direction. So okay, at the end of the class, I will correct means clear this. For now, I have written this answer. Packed media bed is passed through the water. Okay. Now, next question: which of the following relations hold true for specific growth of microorganisms in log phase? So I have already like from whatever explanation I have given in the previous slides, you can actually say this answer. Can anyone have answer? For which of the following relations hold true for specific growth rate of microorganisms in log phase? C, right. C is the right answer. So here you can see for any wastewater. So for any wastewater, you have a wastewater and you provide microorganisms. Initially it will be like in a lag phase. Then what happens, this is the exponential phase, that is the log phase, where the microorganisms will be in a high rate of consuming the food here. Then what happens, then the microorganism will reach in a stationary phase. Then after that it doesn't have food to eat because they already consumed. Then what happens, then they also started eating themselves. Then it will, the dead phase has come. So now we are concentrating on this phase, which is the log phase. Here you see this is the log phase. You can see here the specific growth rate, the growth rate of microorganisms. Mu is at mu max at this particular time, log phase. Okay, so this is the answer. Next, okay, next problem. So I will give 5 minutes break. Then we will start the problem section. You can take 5 minutes break. Then we'll start the problem section. Okay. Okay, we'll start the class. Okay, you can read the question. For a specific strain of microorganisms having maximum specific growth rate, mu max is 4 per day, and half saturation constant Ks is equal to 65 milligram per liter. The specific growth rate mu at 165 milligram per liter substrate concentration will be what? So the values which are given, you can see mu max is equal to 4 per day, and half saturation constant Ks is equal to 65 milligram per liter, and specific growth rate at 165, specific growth rate mu, we have to find mu is equal to what at 165 milligram per liter of substrate concentration. S is equal to 165 milligram per liter. Okay, so this is given, and we have already know the equation. Mu is equal to mu max into S divided by Ks plus S. So put these values here and calculate. Yes, option C is the right answer. Yes. Okay, how do you write here? Mu max equal to 4 per day into S means 165 milligram per liter divided by 165 plus 65. These all are milligram per liter. So this will get cancelled. Then the answer is around 2.867 something will get. Yes. 2.869, 2.8695. So then we can write like 2.87 per day. C is the option. Okay. Next question. So here an activated sludge treatment system is to be designed for treating around 18,300 meter cube per day of municipal wastewater. So this is the amount of wastewater that we have to treat, which is 18,300 meter cube per day. Then with a mean cell residence time of 10 days. Soluble BOD in the influent is 150 milligram per liter. And the desired soluble BOD in the effluent is, this is in the influent and this is in the effluent, it is 5 milligram per liter. Assume MLSS concentration of 3000 milligram per liter and overflow concentration of 10,000 milligram per liter from the secondary clarifier, and consider the following values for the kinetic parameters obtained from pilot scale analysis, pilot plant analysis, Y 0.55 kg per kg, KD 0.04 per day, and a tank volume of 6100 meter cube. What we have to calculate is we have to calculate the oleometric loading rate in kg per meter cube day. How do you calculate? So we have to calculate the oleometric loading rate. So what is oleometric loading rate? Here, how do you calculate oleometric loading rate? We can calculate with mass of soluble BOD divided by volume of the tank. So here volume of the tank we already know. So this much 6100 meter cube. What we don't know is the numerator. So now we'll write the non-quantities to calculate the numerator. So first of all, 18,300 is given, a meter cube per day is given. What is this? This is the influent flow rate. So influent flow rate is equal to 18,300 meter cube per day. And it is given influent soluble BOD concentration. So influent soluble BOD is equal to 150 milligram per liter. Then from this particular we can calculate the mass of soluble BOD in the solution. So that you can calculate by is equal to this one influent flow rate. Let's say we can write like Q, this Q into influent soluble BOD. This is influent. So this SI we can denote SI. So you get the value, then you can put this value in this equation and you can calculate the oleometric loading rate. Do it and tell me the value. So first of all, what is the mass of soluble BOD in the influent? This one, Okay, what is that? 2745 2745 triple zero unit meter cube per day, and S is in milligram per liter. So you have to do one more. What is this milligram per liter? Gram per yes, right. So you can directly write like gram per meter cube, and this meter cube can cancel. This is like gram per day you get, right? So then you have to put this value in the oleometric loading rate equation and calculate the oleometric loading rate in kg per meter cube day. So you can write, you can even convert this. So here it is given kg. So you can convert the gram into kg. How do you convert? You divide it by 1000. So 27,000 means this 30 will go. So 2745 divided by, that is kg per day, divided by what? Divided by this one 6100 meter cube. So when you do it, 2745 by 6100, what is the answer? Yes, 0.45 kg per meter cube day. This is the answer. Everyone got understood? Okay. So we'll go for the next question. The average mass biomass concentration in milligram per liter. So we have to use the previous values which we have calculated, and we have to calculate the average biomass concentration in milligram per liter. How do you calculate this? So this one you can note down the values from this question. Done. Okay. So in continuation of the previous question, we have to calculate the average biomass concentration in milligram per liter. So how do you calculate this? So to start with, we have to start with the total biomass production. Total biomass production. So let's say this is xt, total biomass production equal to um, L naught y divided by BOD influent minus BOD effluent. So what is influent and effluent? What is the difference between influent and effluent? Okay, yes. Yes, right. So that okay, then what we have to find is what is this y is the yield coefficient. So yield coefficient it is given, right? What is the value? Yes, right. Yes, yes, yes. 0.55 kg per kg. Now this BOD effluent, here you see what is the BOD effluent. Yes, 5 milligram per liter. So we have to convert this into kg per meter cube. How do we convert this? Yes, so then 5 minus 3. Then how point double zero 5 kg per meter cube. It is the BOD effluent. This one. And what is BOD influent? This question it is given milligram per, yes, yes, 150 milligram per liter. Then what we have to do is we have to convert kg to kg per meter cube, as we know already. Okay, as we know already, what how we convert 1 milligram per liter is equal to 1 gram per meter cube. So 150 milligram per liter means actually 150 milligram per liter means 150 gram per meter cube. So now we have to convert this particular variable in quantity into kg per meter cube. How? You have to divide with 1000. 150 divided by 1000, right? How do you write? 0.15 kg per meter cube. So now you have the value. So here BOD influent we have, BOD effluent we have in kg per meter cube, and y is the yield coefficient, and L naught also we have. What is this L naught? What is this L naught quantity? You know? Yes, this is the mass of total ultimate BOD that we have calculated. So what was the value? It was the 274. How much it was? 27. Yes, it was here. See this one. 2745 gram per day. So that means 2745 2745 triple zero gram per day. So it is 2745 kilogram per day. So here L naught equal to 2745 kilogram per day, right? So now what we you can just put all these values in this equation star, then calculate the total biomass production xt. Calculate it and tell me. What is the total biomass production? L naught, what is L naught is 2745 kg per day into Y means here Y is 0.55 55 kg per kg is gone, and then divided by um, this is BOD influent is 0.15 minus point effluent is 0.005. Uh, this is in kg per meter cube. So we'll get this xt in meter cube per day. 2745 into point 10 412 yes, which is equal to 10412 this point 068, right? Okay, that you can write meter cube per day. Okay, now average biomass concentration. So here we have to calculate the average biomass concentration in milligram per liter. So here this we can calculate ml is equal to x that we have calculated here, total divided by oleum. So oleum here is 6100 meter cube. Xt is we have calculated 10412 meter cube per day divided by B is 6100 meter cube. So then we getting in per day. Okay, let me 412 0.72, right? Yes, 1.72 we're getting per day. Okay. So how do you, so any unit mistake I have done? L naught Yes. Yes. Where? This one, X, right? L0. L02745 kilogram per gram per. So this one, yes, kg per day. So kg per day we can't convert in that L naught. So this is the okay. L naught here also we got L naught in gram per day. It is milligram per liter. How do, okay? What is the major unit of MLS? Okay, milligram per liter only. Milligram per liter only. So how? mm, Okay, I'm not able to find this thing. L naught. So here L naught. This is L naught. Q. What is the unit of Q? Q here is meter cube per day, right? Then SI milligram per liter. Then convert into gram per meter cube. So that become gram per day. Then okay, I will clear this next class. This thing. But how come kg per day and then okay, okay, this will clear in this next class. This 13th question, B question. Then next question also we'll see how unit things comes here. So next question, food to microorganisms ratio in kg of BOD per kg of biomass day is. The answer we have to mention in kg of BOD per kg of biomass day. So in food to M ratio, F by M ratio, we have to consider the values we have found in the previous the question that we have just solved. So first of all, how do you calculate F by M ratio? So what this is F? F is the food, M is the microorganism, right? So food, food means where we are providing food. Where are the food is coming from, influent or effluent? From where the food is coming? Yes, right, influent. So F means food, F from the influent. So that we already calculated. That means what? We have calculated the BOD, ultimate for one. Yes. Here we have to use this one, this only. The total we have to use. Mass of soluble BOD, total, the flow rate into SI. We have to use the flow rate into SI. This particular value we have to use. Because when I calculate the answer, I have got in the like denoted range when we consider this particular total mass of soluble BOD that we calculated inflow rate Q into influence soluble BOD. So there it is 2745 kg per day. Then average biomass concentration MLSS in kg per meter cube. So MLSS, how much? So that we have to use the answer that we got in the previous. How, what is the answer of the previous question? We got in per day. Actually, in the answer booklet, it was mentioned like 1.72, 1.72 kg per meter cube. Kg per meter cube. So I am confused with how they convert in this unit. Actually, in the booklet, it is given 1.72 kg per meter cube. Okay, consider this only for the next question. This unit conversion I will sort it out next class. Here, consider this 1.72. Okay, this is 1.72. You take it also like kg per meter cube. We will try to solve after this question, that only. So MLSS we have done. Then biomass. Here this is kg per meter cube. It is given. So, how do you calculate the total biomass in kg? Here per meter cube it is given. So, total biomass we have to multiply with the volume, then we can cancel out this meter cube, then we'll get in the amount in kg. How do you do? 1.72 kg per meter cube into this total volume. What is the volume? It is given. Volume is given 6100 meter cube. So this meter cube get cancelled, and then biomass will be 1.72 into 6100. So it is 10492 kg. Okay. So we got in this. Then what you have? You have this particular food in the effluent in kg per day. Kg per day you have. Then what you have? You have the total biomass in kg. So you do F by M, then you can put the value here 2745 kg per day divided by 10492 kg, get cancel and you get the value in per day. What is the answer? Yes, 0.261. And here also we got per day when we cancel out. This here you can see kg of BOD, kg, kilo biomass per day. Here also kg of BOD per kg. So when we consider this also, see, this kg and actually this kg and kgs get cancelling, only per day is remaining. So we can directly write like this particular form also directly, 0.261 kg of BOD per kg of biomass dot day. But here also you know that this kg and this kg is getting cancelled, kg. So remaining this day that we got here. So but here for more understanding, this particular term kg of BOD per kg of biomass is mentioned, this, like that. Here also we'll just sort it out. This you guys understood, this last question. So then now second question, what comes here? Okay. So the first A part is clear, right? First part. Any doubt in this? So here we have considered the inflow rate Q in meter cube per day, and influent soluble BOD, which is influent, it is 150 milligram per day, and the whole is for the influent. So then mass of the soluble BOD, mass of soluble BOD, which is in the influent, we have calculated as Q into SI. Q is the inflow rate in meter cube per day. And then what we have done, we have multiplied with SI, which is the influent soluble BOD in milligram per liter. Per liter, how much milligram of BOD present, that is there. And then what we have done, we have convert into gram per meter cube, right? Gram per meter cube, that means 1 milligram per liter is directly 1 gram per meter cube. 1 milligram per liter is equal to 1 gram per meter cube. Like that we directly done the conversion and it turns gram per meter cube. Then we cancel it, and then we got the mass of soluble BOD in the influent as gram per day. So that is gram per day. So then we have put it in the equation. What is the volumetric loading rate in mass of soluble BOD in the influent? So here mass of soluble BOD in the influent, it will be gram per day. Then volume of tank. Volume of tank is meter cube, right? So okay, this particular answer we got according to the unit we mentioned here. See here it is gram day meter cube. Here gram we got. We can convert into kg by dividing with 1000, right? So this part is clear, right? This part is clear. So only this part. So in this, Sangamitra, you have raised something, na? So some about L note, you have told something. Oh, okay. This L note you have mentioned, right? Okay, so we have put in the kg per day. So if this particular is in milligram per liter, then milligram per liter and milligram per liter get cancelled, and only then the total term will be gone. Na? So if this is milligram per liter and this is BOD is also BOD, we have calculated in milligram per liter. If it's milligram per liter, this will get cancelled, and y also have kg per kg. No, no, not that way. Okay, then I will. Okay, I will talk about this in the next class. This part is clear. Third part. Part is clear, right? So we have considered F and M, and here we have is in the previous question. Here they have the answer was 1.72 this only kg per meter cube only. So we got in per day. How the unit thing I will tell. But so this answer we have considered 1.72 kg per meter cube is considered for the next question, and then we have calculate the F by M ratio. Okay. Okay. So one more thing that we were discussing about this now in rotating biological contractor. So I have checked. So here the answer is B only. Okay, not C. Okay. So here, huh. So in the packed bed media is passed through the water. So not the media, not this particular option is not right. The water is not rotating in the counter current direction. So the packed bed is rotating through the water, which is shown in the figure. So anyone has any comments on this class? Anyone? So you got guys got understood this process? What is conventional activated sludge process? Understood. Huh. Okay. Okay. Ha ha. Okay. Ha ha ha. Got it. Huh. Understood. Okay. Okay. You said like this. Like I have to draw like this, and what is the influence, and what is the? Okay. Okay. Sorry. Okay. Next. Next. Uh-huh. Okay. Okay. Got it. Okay. From next class onwards, I will do that. Yes. Thank you. Something. So this also you also look into it. What gone wrong here in this problem? You have noted down the problem, right? Sorry. Uh-huh. Okay. 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 Ha ha ha. So okay. Anyway, next class I will solve this. The second part how it came. Okay. So then I will talk like this only from next class with the diagrams. Okay. And one more thing I have to discuss. So here, if you okay, so in this, you know that we are using the organisms for our, for treating the wastewater. So, how do you like, um, so from my explanation, what do you think at the end of the food, what the organism will start doing? If the food is not there, what they will do? Okay, yeah, right. So they eat the other microbes. So the that time what we have also understood from the graph which I have shown. So that phase is what? Which is that phase? If they start eating it, then what phase it started? So that is this phase. Decline. Yes, that is the death phase. Okay. So what is the good phase that we can think of for treating our wastewater? What is the phase? Is this one, two, or three? Yes, one is the answer. Yes. And one more important thing, sludge. Sludge means, what do you think? 90 percentage of sludge contains what? Majority of sludge means what it is, what it has. Yeah, most of it's liquid. That means water. Other than water, we can say organic matter. So organic matter here means organic debris and also microorganisms. So other than this organic matter, one more thing is there, which is inorganic matter. So what is this inorganic matter? What are the inorganic matters here? What is the inorganic matter here? Anyone know? So inorganic matter means it is minerals, metals, or non-organic particles. Okay, so sludge means all these things are there. Water is there, and also organic matter, inorganic matter, and we have more of microorganisms. So these microorganisms are mainly used for the treatment of waste here. Then we are transferring into the tertiary tank for the disinfection. What is the need for the disinfection unit? Why we need this tertiary? Sorry. Yes. Yes, yes, right. So, this activated sludge, the whole process contain all these steps. So, each step is important. The primary treatment is important. What is the primary treatment that we have already seen? That flocculation, like we are removing the suspended particles from the big water wastewater, so that our next step will be more smooth than the more smooth. Otherwise, if what do you think, if there is some big particles and particles are present here without primary treatment, we are just transferring into the this our treatment unit. What happens to the treatment unit? So so if there is big particles, big chunks of particles are present, we are not, or for example, in the primary treatment, we are removing the big things from that. For example, if plastic things are there, plastic bottles, plastic covers, or some other materials are there, we are removing the primary treatment steps. So if there is, we are not conducting the primary treatment step, all these things are coming into our system. Even the plastics will also be there. So then this will actually, this if the, for example, this plastic is present in our wastewater, what happens here? That will affect the growth of organisms, right? So the efficiency of our system decrease. What do you think if the plastic is present in the aeration tank from the wastewater? Yes. It will interfere in the whole process. So we have to remove these things through our primary treatment. So also one more thing is there, equalizer. So the flow through our device, we have to make it unit. So before we when we transfer in the after primary treatment, for example, we this is the for time being we make it like that. This is velocity and this is time. Our velocity will be like this. And also, we also, when we see the position, also when we analyze, velocity at different regions will be very different. Now what we have to do is we have to equalize our flow in the system through an equalizer to make the velocity constant for the smooth operation. That is also one parameter that you have to look into it for the efficient process of the system. So that's all about the this activated sludge processes. So I hope that this class, I think you guys all understood. So any doubt is there in this class? Okay, hungry. Yes. So we need see, for example, for understand, like if you consider a wild animal, so just it's a simple. I'm just giving you to understand. So we have some. See, for example, we have a lion. So that lion is not he is in a cage and it has not eaten anything for past so many days. Okay, so it has not eaten anything for past many weeks, then it is very hungry. So whatever you give, whatever you throw, it will eat in a very fast rate. It will eat the it will be like eating so vigorously, like it needs some food. So like that, when the microorganisms don't have proper conditions for them to have food, it will be in a hunger state. So hunger state means these organisms are waiting for the food. So when we give good condition for them, they will their metabolism is very, it will be very high, and it will be started doing eating food very quickly, like it is eating and eating as much as it is getting because it's very hungry. So we need this hunger situation. So we can actually, the for the hunger also, low hungry, medium hungry, very hungry. So we can get this situations by providing proper conditions necessary, and we have all these conditioned microbes. So we can opt anything. If we need to opt for low hungry, we can get it. Also medium hungry, also we can get it. Also we'll get very hungry microorganisms also. What you have to do is you have taken the microorganism, then you are not providing proper nutrient. You are not providing nutrient. You're not providing proper nutrient. So now it has hunger, it don't have food. You're not providing nitrogen, phosphorus, or any other things are not there for them to consume. Also, if there is low do, dissolved oxygen is low, you are decreasing the dissolved oxygen. So at this condition, this particular organisms can't consume food. So this condition also suitable for the increasing the hungriness of the microorganism. Or you can do more aeration. You provide more, aeration. When you provide aeration, this wastewater is more, touch with the aeration. At this aeration means it is actually the low nutrient condition. So all this condition you can provide for a system with the microorganism to make it more hungry. and this particular system you can provide in the aeration tank. So here, this, then what happens when these microorganisms are very hungry? Now you are providing the wastewater. Now this wastewater has the organic loading. So now what happens, it will start eating whatever is it's seeing, like it is eating in a very, very hard, because they are very hungry. So they are eating in a very high, intensity. So that's why it will eat whatever it's seeing as food. It will eat like that. It produce more, this it will eat and degrade the organic matter. So that's what it is done in the aeration tank. Got it? Okay. Yes, aeration means we are providing more, air. So there, if you when you provide more air, means it is what is happening, that it is not, properly. It can't eat also the food in the water. So it is more exposed to the aeration air than the water. Got it? So in this one, yes, yes, low DO, yes, low DO also here, at the low DO also, it can't the we can this dissolved oxygen we can decrease also for uh, microorganisms to increase its hungriness. Dissolved oxygen. Huh. So what here it is meaning is, so it is more, see, for the it needs, for eating it, it needs some stable state, right? Like it cannot, like, if the air is coming, so it is more of this, the force of air. We are providing more air. Understood. Okay. Okay. Any other doubt? Okay. Then this question only I will. Okay. This question I will tell next week, the second part. Okay. So from next class onwards, I will tell you in the diagram mode. Okay. Any other thing? And yeah, the previous class doubt, like, I will take in the next class. Yes. Okay. Okay. Let us wind this class today. Thank you. Okay. Thank you.